All right, let's just quickly go on to our dipole-dipole forces. Sorry to stop you there, but the battery is low, so I'll try and speak quickly. This time, whereas our weak dispersion forces had a temporary dipole, these have a permanent dipole. And we did say that chlorine is much more electronegative than carbon, and so if we think about that in terms of an alkyl halide, that's the name for this, it's a hydrocarbon with a halogen on it, so it's an alkyl halide. This means that our chlorine, because it's more electronegative than the carbon, will end up permanently slightly negative. And the carbon it's attached to ends up permanently slightly positive. Okay? It must be the carbon that it's attached to. The dipole is across this bond. Sometimes people get a bit confused about where the dipole is, but it's located specifically on that bond. Now, there is a little bit of a trickle-on effect to the next carbon because this carbon here is slightly positive. It will trickle onto the next one, but it's not significant. It's not really impacting on the way that molecule will interact with other molecules. So what happens is another molecule can come along like that. And remember that we can't have dipole-dipole forces of attraction unless we have multiple molecules. At the moment I've set up a dipole in one, or we've investigated the dipole in one molecule. We need to have an adjacent molecule that also has a dipole for us to be able to have an interaction between them. So I've got two spots here where this carbon will interact with this chloro group, and this chloro group here will interact with that carbon. Because they're oppositely charged, then they will be attracted to each other. The diagram in the booklet is bad and confusing, and so just ignore it because it's wrong. Okay, the dipole is only across the bond. And it doesn't really matter where on the molecule the halogen is located. It will set up a dipole with the carbon that it's attached to. But depending on where it is, symmetry-wise, is going to then impact on how that changes the physical properties. So a dipole on the end of a molecule is going to increase the boiling point more than a dipole in the middle of the molecule, just because of that ability to bump into each other. It's easier to bump into the end than it is to bump into the middle. So this does increase the boiling point. But it will be greater. So these are still weak, but they are stronger than the temporary dipole. That should be number 2. Okay, and so if we think this is stronger than dispersion. And our last one is given it's still dipole-dipole forces of attraction, but it's got a special name because it is quite significant. And this is called hydrogen bonding. This is the strongest of the weak forces. We're calling them weak forces because they're not an actual bond. It's not like an ionic bond or a covalent bond, or a metallic bond. This is a weaker interaction, but it still impacts on the physical properties of the molecules. So we must have, for hydrogen bonding, we must have hydrogen bonded to an oxygen or nitrogen. I should have really mentioned, it's not only alkyl halides that have dipole-dipole forces, but we can also have our ketones and aldehydes as well, but because we haven't really talked about them, we'll come to them later. So the one that we've looked at so far, the most important thing is an alcohol. Alcohols have hydrogen bonding because we have a hydrogen that's bonded to the oxygen here. And we know that oxygen is quite electronegative, and we end up with charge being shared